record. There we go. But a little better because I feel like last class was not great in that sense. So we're just going to go over some general power transmission stuff, and I'm going to try to go through it quick because we did kind of go over it, some of it last class, and then pop into motors. And motors is what we'll be doing for a little bit because I really want you guys to understand some of the parameters around motors and how to select the right ones. So this is just something that I thought was interesting, and actually these slides are recycled from one of my robotics classes at college, but kind of cut up and cut down. So this here is just kind of a graphic to see. Let's grab a pin here to see energy drop off, which I find pretty interesting. So basically, any system, you're going to have your input energy. And then this is kind of the graphical representation of an energy drop-off. And what's most interesting about this to me, this has nothing really to do with FTC, but is you guys know how like electric cars are supposed to be like the future?
Oh yeah, and the Elon Musk.
Yeah, with Daddy Musk and all that. Well, this energy drop off is interesting to me because it kind of breaks the idea of electric cars a little bit. Not fully, just in moderate terms. And the reason why is because if we have a car for gasoline, right? Let's say basically we've got your, oh, that's not the right, there we go. We've got your oil rig. That goes to, this is a car, that goes to your car, and that goes to the emissions, right? Make sense? If you have an electric car, what you do is you're actually basically just putting in a middleman, and that middleman is a power plant. That's supposed to be electricity. We'll do a battery and we'll just do a zigzag there, battery. And what happens here, so this is the electric car version. What happens here is you actually see more energy drop off. So this down here is a gasoline vehicle, and basically what it is most of your energy goes to your engine, right? And that's because your car's running, it's doing its stuff, it turns into heat and exhaust and all that jazz. You also have some drivetrain losses because drivetrains are never perfect. There's friction, stuff like that, so those get turned into thermal energy. Parasitic losses is like the extraneous systems in your car, so your alternator, your water pump. So a little energy has to go to those to keep them running. Idling has a little bit of energy go to it because your car has to keep running. And then your actual energy for movement, the energy that actually goes towards your car moving, is what comes out over here. And you can see there's a huge drop off, right? What's interesting about the power station is that's this one up here. So imagine before we even get to this input energy, right? We had to go through this diagram. And so what that would mean is here's the energy that goes into the power station, whether it be coal or oil or, you know, whatever you put in. You got heat losses to the environment, so some goes off as heat. Some goes into the power station itself to run the station. Some goes to transmission, which means the conversion of power. And then this is what's actually delivered to customers. And so this output over here is the same as this input over here. And what happens is, you know, if you imagined this bottom diagram just kind of pasted on at the end over here, you actually see more losses because you've got, you know, your, man, I cannot draw an arrow for the life of me. Your engine losses, and then you've got your drivetrain losses, then you've got your parasitic losses, idling, and then you have your output, right? This is just a cool, interesting graphic that I thought was I thought was kind of cool. basically it just shows that the consumption of energy is not as simple as people think it is. And sometimes there's a bigger picture than just electric cars are cool, you know, although Musk would like us to think so. And I'm not against electric cars. I like electric cars, but you have to make sure that where the power is coming from is actually a good place. If it's solar, if it's geothermal, if it's hydro, those are great. Wind power as well. But if they're just running a power station and then you know, and then pumping it into your car, well, ripperoni. All right, that was just an interesting thing. It doesn't have really anything to do with the class other than we're talking about power transmissions. So first off, this is just what we're talking about today, and we talked about it a little bit last time, is gears. You've got basically your basic gears types, and then you've got planetary transmissions. You guys have probably heard of planetary gearboxes. And then we're going to talk about a little bit about sprockets and chains a bit more. So this is stuff we talked about last time. Do you guys remember this?
Mm-hmm.
Cool. Yeah, so basically you've got your gear ratio, which is E, and these slides and everything are going to be posted along with the recording of the class. So if you ever need to come look at these for anything, feel free. Basically, I try to get it so that I could show you what everything stands for a little bit better. So basically, DRS is drivers and DRN is driven, which is drivers are the one hooked to the motor and driven are the ones furthest away from the motor. And then basically what this says is you can either define E, which is the gear ratio, the gear train speed ratio, whatever you want to call it, with number of teeth or angular speed or torque and efficiency. Efficiency, sometimes you just ignore, but usually you should include it. And that's what's down here. It's just saying that all of those things are the same, okay? So that's just very, very quick review of what some of the stuff we did last class. This is a cool diagram, which I started talking about some of this stuff last class, but I don't know if I got the points through. This is a cool diagram just showing different parts of a gear. And a lot of this has to do with the math to create a gear, which I guess, Maxim, you might be familiar with a little bit now. I don't know if you had to actually do any of that for the little gearbox that you made.
What do you mean?
So there's math that you can use to basically decide how a gear is built. You can also use CAD. One thing that I wanted to specifically make sure you guys understand, and I touched on this last class as well, is right here, you see this circle going through? That there is the pitch diameter or the circular pitch, whatever you'd like, either one of those. It's got lots of names. They all have to do with pitch. So it's pitch circle, circular pitch, pitch diameter. You can see some of them here. So this is pitch diameter, circular pitch, and pitch circle. They all mean basically the same thing. And that is this line here, which is between the outer diameter of the teeth and the inner diameter of the teeth, okay? And the reason that matters is if somebody asks you the diameter of the gear, the pitch diameter is the one that you want. So you don't measure to the bottom of the tooth, you don't measure to the top of the tooth, you always measure to the pitch diameter, which is typically about the middle of the tooth. The reason you do that is because if you see where these two gears meet here, if you represented the gears by circles, the pitch diameters only touch in one spot, but the outer diameter of the teeth, they touch in two spots. You see right there and right there. So basically, if someone needs the diameter of a gear, you always want to give them the pitch diameter, okay? It's also useful for finding your centers. You're going to have to do things where you find center holes for gears, also based on the pitch diameter. So that's another quick thing. Just another review of last class. Okay. Oh, like I said, I recycled some of these slides, so there's a bunch of these. Is that all good? I think that's good. Okay. All right. So things with gears. You're not going to need to know this a lot, but this is some of the gear math stuff that I was talking about. So diametral pitch. It's basically how many teeth are there. Oh, I can just draw on this. That's cool. How many teeth are there on the per diameter, kind of, which you can kind of see number of teeth of the gear over pitch diameter. So it's basically how big is the gear and how densely packed are the teeth. So do you have a bunch of little teeth, or do you have a bunch of, or not very many big teeth, right? So it's always an integer number. You can't have half a tooth. That doesn't make any sense. So and they're always divisible by 4, at least standardly. So, 32, 28, 24, 20, those all work. And diametral pitch is P, okay? Capital P. So larger larger the diametral pitch, the smaller and weaker the teeth. So basically, if your diametral pitch gets bigger, right, you're going to have smaller, more densely packed teeth, but they're more likely to break because they're smaller and not as beefy. Reason that's important is if we were to do a free body diagram on a gear, right? Let's see, this is our gear and here's a tooth, and we can pretend there's more teeth, but all we care about is one tooth, okay? If we were to draw the free body diagram, if there was another gear interacting with it, it would be causing a force on that gear this way, right? And we could basically do statics, which is what we did in the first section of this class, to find out if this gear tooth would break. So lots of gears will come with ratings as to whether or not, or what their breaking stress is. It's called their shear stress. Shear just means to the side. And basically, if the forces that you're putting on that gear tooth are more than it can take, your gears are going to break, or they're going to grind, or they're going to shear, those all mean the same thing. But it is important that if you have something quite heavy, that you check to make sure your gears are going to be able to handle it. And it's just rule of thumb that if you know it's going to break, you need to try to make the diametral pitch smaller. So fewer teeth, bigger teeth. Pressure angle, it kind of matters. The main reason it matters is because it's one of the things that causes two gears to mesh. If they have different pressure angles, they won't mesh. If they have the same pressure angle, they will mesh. So more transitions, we love them. Okay, so spur gears are just what you guys are used to. They're the normal kind of gears. It's when you think of a gear, it's a spur gear. So spur gears have standards. Typically, like 12 tooth is the smallest that you'll get, and they can go up from there, which is that infinity there. They are always like standard sizes that you'll see. So you'll see 12, 16, 30, 42, and I think 75 is up there. Yeah. But they always have a integer number of teeth. Do you guys know what a pinion gear is? So rack and pinions. The pinion is the spur gear, and then the rack is like a flattened out gear almost. Pinions can be smaller, and sometimes they're even smaller than 12 tooth, though it's rare. I think I've seen some in FTC. Go ahead.
Is it like a gear with like a tread kind of thing?
So a rack and pinion, if you imagine, this is a gear. is like this. Okay.
Oh, yeah,
And these two guys mesh with each other so that when this rotates, this moves in a linear fashion. Okay. So sometimes the pinion, which is this little guy, little spur gear, can be smaller. They're usually pretty weak because they're tiny. And if they have basically the smaller pitch or pressure angle, they can break pretty easy. So you kind of have to be careful with them. If they have, and this is important, if they have the same diametral pitch and the same pressure angle, they will fit, they'll mesh. So this is the diametral pitch. Oops, well, there we go. And pressure angle.
I don't actually know what pressure angle is. What is that?
Yeah, so that was on the last slide.
Okay.
Basically, down here, oh, sorry, 2 slides back. Boink. Oh, gotta love these transitions. There we go. So diametral pitch is just your number of teeth divided by your pitch diameter. The pitch diameter is, I don't know if you saw that, Jude. If you have a gear, you've got the under part of the tooth and the outer part of the tooth. The pitch diameter is in between them, okay?
Yeah, I know.
And it's typically the true diameter of a gear.
Yeah.
But so that's how you find diametral pitch, which is P. Pressure angle, there's typically only 2. It's either 14.5 or 20. Pressure angle is basically the angle of the tooth. And we can go back and look at pressure angle itself so you can see. Oh, there we go. So pressure angle is right here. And basically, let's see if I can get this. There we go. Yes. There's a few different places that you can find it. I don't know if they have it on here, and it's no. But basically what it is if you take a point from the diametral pitch, or the pitch diameter, the pitch circle on one tooth, and then draw a line through the next tooth where it's perpendicular to that tooth. There's the pressure angle. Gears will always say their pressure angle. It's either going to be 14.5 or it's going to be 20 degrees. It's one of those two. I think 20 is typically more standard. 14.5 is weaker.
20 is what, like,
I would imagine that most of the gears are 20.
20 is just kind of what I put whenever I design gears. So yeah.
Skip through these again. So yeah, you can see down here, it's typically one of those two. This is true though, it is more efficient. So if you're doing like a low load application, 14.5 can be better. But it depends on what you're doing. Oh, this is actually important real quick. And I forgot to mention it right here. When you're looking for basically the axle separation of 2 gears, and you can see that over here, marked by D. It's pretty easy to get. All you have to do, so D, which is the distance between those 2 axles, is going to be your total number of teeth divided by P, which is your diametral pitch, divided by 2, okay? So if we have a 16 tooth gear and a 42 tooth gear, it's going to be 16 plus 42 divided by 24, which is the diametral pitch of these gears, divided by 2. And that can tell you exactly how far your axles need to be from each other for these gears to mesh perfectly, okay? Which in FTC, that's a little harder to do just because sometimes you're using like the Actobotics rails and stuff. But if you're making your own siding and stuff like that, your own panels, this is a good thing to know because it's a way for you to mathematically check that your gears are going to mesh well, okay? So keep this in mind whenever you're designing transmissions because
Yeah.
it's a good way to double check.
Kyler taught us how to do that in his
Yeah.
class.
You can also use CAD just to do it for you, but if you want to check it mathematically, that's a way to do it. Okay, worm gears. These are some different types, a little weirder gears.
Right.
Good things about worm gears, and some of you probably know this. This is the big one. They're anti-backdrive. They won't backdrive. So if you have a driven worm gear and a driver, if the worm gear is the driver and the spur gear is the driven, your system won't backdrive. It'll always go one way unless you power it the other way. Okay. So their helix angles, they're a little different than the way the spur gears work. So we will say that a spur gear has 50 teeth because it has 50 teeth on it. A worm gear is defined not by teeth really, but by helixes. And they're still kind of called, they're usually called leads. This one has 4 leads. And basically what it is if I took a circle with 4 like sticks on it, and then I just like twisted that circle around, you can kind of see that the number of leads is how many starting points there are on that worm gear. So if there were only 3 to start off with, 3 like that, then it would be a 3 lead worm, and they'll twist around each other in a helix pattern, kind of like that. It's hard to draw. You get the idea. They are extremely inefficient. What that means in terms of like seeing things, you guys will know from using them probably. The more teeth there are on a gear, the faster and better it runs, but the more likely it is to break under load. Worm gears are pretty good in terms of torque usually, and they don't backdrive, but they're really slow and they're really inefficient. They got to put more power into them to get a similar result, right?
Yeah, worm gears are like horrible to work with in FTC. Like
They
very
can be
reliable.
unless you need something like if you're doing a climbing challenge and you don't want your robot to like, if you're using a drum like a winch, right?
Yeah,
And you want it to go up and then not slowly fall back down, then a worm
yeah.
gear could be
We
good for that because it won't backdrive.
well, yeah, we did that, and it still like I just wouldn't recommend using a drum for climbing.
You can, and we're going to go over this later, but you can do the calculations to make it work well. Okay.
Yeah, I mean,
If you just
just
pop
have
a
to
worm
use
gear
much
on there,
faster
it's going to be sad. The
motor.
problem with them is that their efficiency is somewhere around 0.25 to 0.75. They're not efficient,
Yeah,
but they are useful for certain applications.
and then
For worm gears, real quick, the gear ratio, E, which is our gear ratio, is the number of leads on the worm divided by the teeth on the worm, or on, this should say spur gear. So basically, this example here is for this diagram. So basically, we got 50 teeth on our spur. We got 4 leads on our worm. And so our gear ratio E is going to be 4 divided by 50, which is 0.08. So that's useful if you want to know your torque to speed ratio, right? If you need a high power application, don't use it. And you need to make sure it's really locked in and mounted well if you're going to use it, because it does system.
Hey, David.
Yep.
Since I'm not officially an FTC and I have not had to deal with a lot of this stuff, I have no idea what any of this means. So I'm basically just listening.
So basically, this thing here at the bottom.
Well, yeah, I've seen worm gears.
Yeah. So technically, this typo over here is not a typo. Technically, the spur gear here is the worm gear, and the little thing down here is called the worm. So, but for simplicity's sakes, I just call I call the worm a worm gear and the thing connecting to it a spur gear, because that's what they are. But basically, what this means, Carson, is that if you want something for high power applications, so high torque, high speed, worm gears are not the way to go. If you want something that's going to be relatively low power, either low torque or low speed, usually low speed, and you don't want it to backdrive, meaning you don't want it to so you power it one way, so like you're winding up a winch, right, to make something climb, and you don't want it to, when you turn off the motor, start to go back, right? You don't want the weight to pull it back out. Then a worm gear can stop that. It's anti-backdrive, so it won't undo the thing that you did, unless you power it in the opposite direction. You turn the motor back on in the opposite direction, you can get it to go down.
Or you can just use a differential.
Yes, you can also use a differential.
Because if you use a differential in a certain way, you can actually make it act like a worm gear, and you can't have it go back.
Yeah, you actually can do some other stuff, and we're going to look at a couple of those in a bit. But basically, worm gear is a type of gearing, a type of transmission that is anti-backdrivable, but it is low efficiency, and efficiency just means basically you put so much power in, you get so much power out, right?
I know
So,
what efficiency is.
Yeah.
So inefficient because like the gear can just slide off under too much pressure.
The reason it's inefficient, if you have, let's say, here's two teeth of two gears, right? Of two normal gears, two spur gears, they put forces on each other basically perpendicularly, right? If I have the lead of a worm gear and I have a tooth on that worm gear, right? The worm gear can put a force on it, but that force is going to be at like a shear angle. It's going to be at a pretty bad angle, right? And from what we learned from statics, the two components of that force, the one that's going to be going in the direction of actual movement is going to be much smaller than it would have been if it were at a 90-degree angle, right? Because some of this angular force is going up into the gear and not actually doing anything. Does that make sense?
Yeah.
Yeah. So that's why worm gears are pretty inefficient. The statics just don't work very well for them. So this is just to show you how worms work and screws in general. Basically, you've got your lead and your pitch. This shows different types. So you can see single start, double, and triple. You can see this one only has one lead start. This one has two lead starts. And this one, you can't really see the third, but there's one here, two there, and there's a third kind of in the back. Oh, you can see them up here. There's 1, 2, and 3.
I think most of the ones for FTC only have one lead start.
That I would imagine so. But when you're doing the gear ratio for it, you do need to know the number of leads.
Yeah, like this is like the tooth number, right?
Oh, yeah. So it's basically over number of teeth. So your gear ratio, E, is your number of leads divided by the number of teeth. And the teeth is the spur gear that it's connected to, right? So you do need to know your number of leads if you want to find your gear ratio. The pitch is how angled out are the leads. So you can see this one has a pretty shallow pitch. This one's got a much more angled pitch, and then this pitch is pretty far over. Basically, it's the angle of the lead coming out. So this would be a shallow pitch, this would be a not so shallow pitch, and this would be a steep pitch. And that's basically just the lead going around, right? The less shallow the pitch, the more efficient it will be, the faster it will be, but there are other considerations, and basically that's how much force you're putting on the worm, right? So you can end up generating more heat. You can break your worm, you can break your motor. There's all sorts of things. And sometimes certain pitches can only go with, like, there's there are pitch and lead constraints, right?
And in FTC, if a single start gear, like worm gear, is meshed with like a 20 tooth spur gear, that's gonna, like, if you hook that up to a 60-to-1 motor, that's gonna make a really high ratio. But
Yeah.
most worm gears for FTC can't handle that amount of weight that you're going to be putting on that.
So a lot of them, if you put too much load on them, it'll just cause the motor to bind. And the reason there is your gear ratio here.
Yeah.
You can figure out how much torque is being put on the motor using your gear ratio E. And if it's more torque than the motor can handle, it's not going to work.
Well, also just the gears can't handle that much torque.
Well, the gears could break.
It's not the gears, it's the hubs and stuff attached
yeah,
to
I mean,
them.
they
Like
can
FTC
break
hardware
for sure.
just isn't strong enough to use worm gears to their full potential.
They can definitely break for sure. If it's binding, if it's just stopping and not breaking in any spot, then that's the motor. This is something that I mentioned earlier, planetary gears. We're not going to go into them too much, but you guys have seen them. Your motors use them. The gearboxes on your motors. So you say you have like your Andy Mark 30-to-1, right? It's probably got a planetary in it. And planetary gearboxes are basically just, they invert one of the gears. That becomes the ring of the planetary gearbox. And then you've got your planet gears, which are these outside ones. You got your sun gear, which is this middle one. And what this is it's basically an easy way to have an efficient system with a good reduction. So basically, they're used in motors a lot. You probably won't use them in your own like applications so much. A nice thing about them is that, so like let's say this middle motor or this outside is going this way. We got to draw some boys. Basically, they all spin in the same direction, right? So this one would roll this way, this one would roll this way, this one would roll this way, and meshing would all work out. Not a huge deal. They're in your motors. I just wanted you to see them. There is some cool math to do with them. If you want to, you can look them up. They're more efficient just because you have 3 points of contact instead of 1. And everything's locked in a little bit more. Planetary gear train, so speed reduction. The ring, the outside, is just a casing. The sun is the input, so that's like your motor shaft, and the carrier is the output, which is the whole thing. I think labeled back there, yeah, basically the carrier is this guy, the arm. Let's go. Oh, that's the wrong thing. There we go. Anyways, to do the gear ratio for them, and you guys probably won't do this, but since they're in your motors, it might be useful, is the number of teeth on the sun, which is the middle gear, divided by the number of teeth on the sun plus the number of teeth on the ring. Okay, so those middle gears don't really matter other than they connect the two. Okay, and I think that's pretty self-explanatory. I don't think I need to draw that. Does that make sense? Cool. Works basically the same as the others. All right. Chains and sprockets are a little different. So ANSI is standard stuff. It is like the standard, whatever you want to call it. It's the standardization. Chain number. Whenever you look at a chain, it's got its number. The first one is going to be its pitch in 1/8 inches. The second digit is going to be basically what kind of chain it is. So is roller chain, lightweight, or bushed. Those just mean different things about the chain. They're not super important. Roller chain These middle segments roll. Lightweight means it's lighter and cheap. It could break more easily. And bushed means they're kind of like reinforced. They have bushings in them. An example, yeah, so this one, basically number 25 here. So you might see like a number 25 or a number 35 chain, right? Basically that means it's a 1/4 inch, it has no rollers, and it's bushed. Okay, so that's just kind of the way chains are labeled. I'm not a huge fan of it, but you know, I'm not the one who decides. So I don't think I feel like that's pretty self-explanatory. A number 35 chain is 3/8, so it's just 3 times 1/8. You get your what the pitch is, which your pitch is this guy. And it doesn't have rollers because it's got a 5, so it's bushed as well. Important boys down here. I don't know if you'll ever need this for FTC. It is useful in FRC, which is strength, the working strength of the chain. There's working strength and there's breaking strength. Those are different, and they're importantly different. Basically, every chain number has a breaking and working strength. So if it's a number 25 chain, it'll show you that its working and breaking strength are these. So its breaking strength is 875 and its working strength is 140. Basically what that means is 140 pounds is what you should run it at. However, technically you could run it past that, and you could run it all the way up to 875, but if you do that, it's gonna break at 875. You almost never get near the breaking strength, because if you do and you like hit a bump and it just tugs the chain a little bit, that impulse force will snap your chain. The higher the first number in the chain, the higher these numbers are going to be because you're dealing with a thicker chain. And basically, working strength has to do with its industrial life and its life expectancy. That is assuming you're using it at its working strength. So it's saying if you run it at 140 pounds, you'll see on its spreadsheet that it'll last this long, which is more important for industry, not robotics challenges. But the pitch of the chain is basically the distance. It is useful because it's what you use with the sprockets. There we go. I think most of you guys know this, but basically chains work in a couple ways. There's master links, which are these guys, and there's half links, which are these guys. Oof, my nose. The master links are how you connect chains if you've got a broken chain or something. They connect inner to inner, and I mean, you can see how it works here. Basically, it's just, and it's like a link that is separated from the chain, right? It's just a little guy by itself. You can pop it into the chain and connect a chain together. They are not as strong. They're 75%. The reason why is because these boys are held in by this little clip pin, and so they're just not as strong. If you're ever using them and you have like a number 25 chain whose working strength is 140 and you put a master link into it, then reduce the 140 by 75%. Basically, it's the phrase like a chain is only as strong as its weakest link. The master chain or the half link is the weakest link. So yeah. Half links, they connect inner to outer, which is over here. So if you ever need to connect an inner piece of a chain to an outer piece of a chain, you'd use a half link. There are reasons you need to do that. You won't see them mostly in FTC. You'll probably see master links in FTC if you're using chain. They're 65%. So again, you reduce it to 65% if you were using one to know that your chain's not going to break. So quick things for chain design details. Sprocket sizes, similarly to gears, have standards. Gears are basically 12 tooth and up. However, sprockets, you're usually not recommended to go higher than 75 tooth. Why that is, it's really just because there's no, like, if you're getting bigger, your chain, if your sprocket gets bigger with more teeth, right, your chain in relation to the sprocket is smaller, and it's more likely going to break for your application. You're putting more force on it because it's a larger diameter. So 75 is kind of the top that is recommended, just because that keeps your chain ratio to your sprocket size pretty good in terms of not breaking your chain. The smaller it is, the less vibration you're going to have. That's sort of sensical. You got this big diameter, it's going to wobble. And if things do vibrate, there's going to be more wear and tear on them, as you would assume. If you have larger leads, you're going to have chain loss. That's not a big problem. And ratios should usually be kept less than 7-to-1. Reason for that is the forces in the chain, basically. And it has to do with, basically, you can see here the chain angle. If I had a tiny little guy right here, that chain angle would be really steep, and the force on the middle of the chain would be higher and is more likely to break. Basically, it's just don't stress your chains. So keep it less than 7-to-1. Keep it between 12 and 75. Chain wrapping, basically this angle here, you can see where the chain connects with the sprockets. That is the chain wrap angle, and 100-degree minimum is standard because you don't want to, say if you're kind of the same example as here, but we'll redraw. If I had this, or I guess this, and my chain went around here into this guy, right? The tooth on this chain might actually pull the chain inward and tug on the chain as it's going by, which you don't ever want, because you're, 1, putting vibration on the chain, 2, pulling on the chain, and 3, stressing it. All of those are bad things. So basically, you want your angle of wrap to be 120 or smaller. So you can imagine it could be, like, let's say 60, and the chain would only wrap to here. That would also be good.
This doesn't apply to belts, does it?
Belts are similar, but not the same. The chain wrapping doesn't apply so much to belts because it doesn't catch. But you still are putting more strain on the belt.
Yeah.
So you can do it. It's not as bad, but it's still not recommended to go too small. And basically, the chain wrap is important because it can sometimes change your chain routing. So if we had this example up here, right, we have a really big guy and a really small guy, and we want to link these guys together, maybe we'll put a chain or a gear out here just as an idler, just to pull it so that the angles are okay, so they're not catching and they're not straining anything more than they need to. Let's see. Yeah, so designing an adjuster is really good, and actually this is a good thing for FTC as well. If you've got a chain, and we did this Lucian B. Maxwell's year, that first year, similar to this, if I have sprocket, and I'm going to put a chain between them, it's a good idea to put a another sprocket in, or just an idler, that is on sort of a rotational mount. And the reason why is because if I put the chain around here, right, this guy right here is not actually adding anything to the system because it's an idler. It's just spinning freely. But if you rotate this up, you can tension your chain more easily. And the reason that's important is because chains are of fixed length, right? You can't make them like if your pitch is, I don't know, 0.5, so that's the length of one link, right? And you add all these links together, you can never get a 0.25 on your number. So like I could have 1, I could have 1.5, I could have 2, but I could never have 1.75 because the chain is not that small, right? If you put in an idler that is an adjuster sprocket it doesn't add anything to the system, but you can change it to tighten your chain. Those are always good because they make working with chains so much easier. So if you ever use chains in your FTC robot, it's always a good idea, especially if you're gonna need to tighten your chain for any reason, to just pop in an adjuster somewhere. It could be tiny and it could have a very small range of adjustment as long as it's enough to get that chain tight. Does that make sense?
For if you want to use spurred gearboxes, you can just like turn those to tighten it.
Yeah, kind of.
Yeah, that's what we used to do.
Yeah. So basically, it's just adding in a tensioner for your chain. All right. These are general suggestions, and they are good suggestions. So basically, big things are if you have your motor and you have an option, basically, right? You can either say this motor is rated for 10 Newton meters of torque, okay? And you have like a 50 Newton meter, actually no, let's say it's smaller. Let's do a 5 Newton meter task. So you've got some sort of weight. I don't really care what it is, but you need to lift that weight, right? And you want to lift the weight as fast as possible, but you only need 5 Newton meters to do it. You could either lower the voltage on the motor, right? Run it at a lower voltage so that it's not running at full speed. You know when with the drill battery, how if you press it a little bit, it'll run slower? Same idea, you're just putting in less voltage. You could do that, or you could gear it. And if you gear it, put a big wonkin' gear on this and a little tiny gear, and then your output of that gear is what hooks here. You can run that faster with more power to make this guy go up super speedy than you ever could with the motor alone. And so basically the idea of that is control your top speed with gearing and not by reducing your voltage. You never want to lower the voltage on your motor when you could just gear it better. You know, if you just gear it right, then you can get way more out of your system than by using the wrong motor. So that's a very important thing right there. Keep that in mind when you're building a system. And we're going to be talking about motors later, but and how to select them. So this will become more important then. Another thing is to avoid powered anti-backdrive. So basically, if you have your robot and it's driving up a thing and it's got a hook on and it's on a winch, right? You could either put a worm gear in, which you know is not going to backdrive, or you could, I don't know, let's just pretend this is a motor. You could just put a motor in and keep powering that motor. I'm sure you guys have seen at FTC competitions, robots that climb up, and when the timer ends, they just slowly go back to the ground. It's really funny to watch. What they're doing is they don't have a system that is anti-backdrive. It's powered, so they're constantly running that motor. Problem with that is the motor that's in there is going to die and release all of its magic smoke. It's gonna burn out and be sad, or it's at least gonna get hot and not last as long.
You could also use a lead screw for your climbing
Yes, and
mechanism.
we're going to talk about some other versions of those as well. But basically, if you can do a mechanical anti-backdrive instead of a powered anti-backdrive, always do the mechanical. Put the load not on the motor. That way the motor lasts longer and is a-okay, and your robot doesn't fall at the end of the match. A lot of FTC teams do that, and I think it's just they don't know. Another thing.
Well, a lot of like really good FRC teams do that too, like
Yeah, they do.
1619, 118, 254.
I'm not sure why, honestly.
It's
But
just faster probably and stronger.
fair enough. Another thing is that chains are efficient, but gears are compact. So if you're ever trying to decide between the two, right? That's a good thing to know. You don't ever want a gear train that goes all the way across a thing where you could just have chains. The reason why is basically chains, they have, trying to kind of show this, they have all of this contact, right? So if you have a chain here, they have contact with teeth all along their wrap on your, so let's say you have a wrap angle of 120 degrees, right? All 120 degrees of that, they are touching teeth, right? Meaning they are all applying force on those teeth. So it's a whole bunch of little forces, right? A gear, one tooth hits one other tooth, sometimes two teeth, okay? So basically you have two little forces versus like 40, right? Meaning more of the power gets transferred through a chain than does a gear. However, chains take up a big amount of space, whereas gears take up a little amount of space. So if you need a smaller, compacted thing, use gears. But if you want more efficiency and you don't really care about compactness, use chains. They are better in that term. Does that make sense?
Mhm.
So that's the end of this one. Yeah, I'm going to discard those. Those are just the generals of power transmissions. Nothing in there requires really any, I mean, there's a little tiny bit of math, but it's basically just division. I just wanted to cover those a little bit because I felt like last class I didn't have things prepared as well as I would have liked. So I wanted to go over some of them again. We're going to start motors today. Yeah, let's see. We're going to start motors today, but I don't think we're going to finish them because there is a lot to do on them. So let's go. Make sure to ask questions if you have them. Also, I apologize for the transitions. Like I said, these are recycled slides. So, blah, 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 blah. Let's get these in here. There we go. All right. Basically, basics of motors. There's electrical power and there's mechanical power. Important things about them: power, which is also big P. I know there's a lot of letters that are used multiple times, is equal to the volts times the amps, which really I should write an A or an I there for current, but it's fine. Or it's equal to work divided by time, or it's equal to angular speed, I don't know why I wrote it up there, times torque.
I learned about the weight times time one with power a couple years ago, so that one's what I'm most familiar with.
Yes, work divided by time is power, and work is just force times distance. There we go. So the reason these are important is we're going to be looking at motors, and motors are electromechanical. So a lot of times you have to relate the electric version of them to the mechanical version of them. Okay? So what you can tell from this is basically the more voltage, the more power. The more amperage, the more current, the more power. The more speed, the more torque, the more power. Makes sense. So if you're running something at a certain voltage and a certain amperage, then your torque and speed basically become inversely related. If your speed goes up, your torque goes down, or if your speed goes down, then your torque goes up. Okay, that's something that most people know, but they don't exactly know how it works. An example here for just electrical power is if we have a sim motor, which is a type of motor. It's running at 40 amps, and you know that it's outputting 480 watts of power, then you know its input is 12 volts because 12 times 40 equals 480. Similarly, down here, if we have a sim, same thing, 40 amps, 12 volts. If it's going at 3,800 RPM and it's putting out 6.15 inch-pounds of torque, then it is doing 275 watts of power. That's its output. Then another important thing here is what these two things relate to. When you're talking about a motor, the electrical power is its input and the mechanical power is its output. Okay, so you're always relating those two things. So basically what you can see here in this example is your input is 480 watts, but your output is only 275 watts. Reason for that is motors are not perfectly efficient, so there's energy drop off inside of them. And that's all thermal and friction and stuff. So I don't know if I want to do these questions because I kind of like to get through things quickly. This one's pretty easy. Not easy, but simple. You guys aren't going to know the answers to these. I just want to know what you think. So when operating at their highest mechanical efficiencies, motors in general will either create minimal electrical power, create about 60% of their max power, or create maximum torque. Which one do you guys think is right? I don't expect anyone
B.
to know the answer. Huh?
B.
Okay, so we've got Carson on B. Jude, Maxim.
Sorry, what is B?
Oh, what is B?
No, as in Jeopardy.
Oh, good. Maxim, Jude.
I think it's B as well.
Okay. Maxim.
I'm gonna go with B.
Yes.
Also.
All right, cool. So yeah, you're all correct. It is B. They create about 60% of their max power. And we're actually going to look at some cool, I know it sounds weird, but some cool graphs about that. I don't really want to do that. We're going to go over it in a bit. We're also going to go over that, so that's fine.
Wait, what was the answer?
B was the answer to the one that we did. You're all correct. So this is just a quick problem. It is a little bit of math, but it's just enough to get us started. So basically we have a problem, and this is more similar to FRC numbers, but it can be used for FRC or FTC if you just make the numbers smaller. So we have a 140-pound robot. It needs to climb 5 feet up in 5 seconds. We're going to use a cable winch to lift it. How much net power do we need? Someone get us started. Anybody? I need to come up with like prizes for whoever gets the answers out first. Or at least whoever tries first.
So
I'll think of prizes for next class.
okay, so for power,
So I just wrote the power equations.
right. Oh yeah,
Another important one is work equals force times distance.
Oh, okay. So would work equal 140 pounds times 5 feet?
Yes, sirree.
That's so smart.
All right. And then what would you do?
Would you then multiply it to get the work?
Yeah, so basically, yeah, it would be 700 pounds per foot is the work. And then what? You have work. What do you do now?
You divide it by 5 seconds.
Yep. So pretty simple. You got work, which equals 700, divided by time, which equals 5 seconds. And that is, I don't know, 100. Oh, it's 140. So yeah, we're good. Because it's 5 feet in 5 seconds, it just goes back to what it was, which is perfect. Boom. We have power, and power is in watts. Usually you have to convert, but in this case we don't, so we're good. So yes, you need 140 watts of power, mechanical power, as your output to get this robot, which weighs this much, to climb this far in this amount of time. Does that all make sense?
Well, then why did we do the equation?
Well, these numbers worked out nice. They may not. Because it was 5 feet in 5 seconds, it works out well.
Okay, I thought you just ripped us off. I was like,
no. If it, let's say it was 140 pounds in, I should probably put units, in 15 feet in 5 seconds, then it would be 140 times 15 over 5 instead of 140 times 5 over 5. In this one, the 5s just cancel out and it becomes 140. This one, it would be 3 times 140, which is something or another. 2, 3, 4, 20. Nice. Anyways, so yeah, this is important though, because let's say your FTC robot weighs 20 pounds and you have a climbing challenge and it needs to raise 3 feet in 4 seconds, right? You could find out how much power you need to do that. Okay.
Should we go ahead and solve it?
Huh?
Should we go ahead and solve it?
Yeah, sure. You guys want to?
Sure.
Yeah, let's go ahead and do it. So what would we do first?
20 times 3.
Yep. 20 times 3 equals work, which equals 60. And work divided by time. So 60 divided by 4. Why did I not do that in my head? 15. I don't know why I couldn't do that there. So 15 watt. Boom. Much lower power consumption, but still. So yeah. So you could say you need 15 watts of power for that. The nice thing is, if you know your mechanical output, you can choose the perfect motor for whatever you're doing and know the gearing that you need. So in this one, we have some example motors. You guys don't use very many of these, but you might have seen them or be familiar with them, especially if you've seen FRC. Sim, Mini Sim, RS500, and Tiagene. I think we usually call them Tagene, but basically, Tagene is a window motor. So like, those like the motor that makes your window and your car roll down is basically the same as this. It's called a window motor. RS500 we literally never use. Mini Sim and Sim. Sims are these big chunky boys, and Mini Sims are just the little versions of them.
Now we also have brushless motors.
Yes, these are for motors? These are typically for FRC. FTC, you guys specifically are probably mostly going to be using Andy Mark, and I'll pull up some Andy Mark sheets for what we're about to look at as well, just so we can compare. But
we've actually switched over to modern robotics mostly.
Oh, really?
Yeah.
All right, well then we'll pull up those. The Matrix 12-volt DC motors.
It's on the Go Build a website. We use those.
Well, we'll pull up some sheets for those then. Basically, these are just some quick example sort of stats for these motors. So Sims have a 340 watt max, and it's suggested that you run them at 220 watts at 30 amps. Okay, so this portion here is the suggested. This portion here is the max. And then we can see basically the rest of these. So if you look at them, they descend this way. The reason why is the motors get smaller and or less efficient. Like the Tiagene, I don't know how to pronounce that word, but the window motors, they have a worm gear in them, so they're less efficient by a lot. So you can see they only have a 50 watt max. But basically, these are just some example stats for motors. They get big slash efficient to small slash inefficient. Okay. So let's say we chose a sim motor, right? And a 1 to 30 gear ratio. Okay. That means the torque is increased by a factor of 30. Okay. If we showed that, it would be like we could show it in the gear ratio format with E, but we don't need to. And we're limiting the motor to 30 amps because we're concerned about heating up that motor and breaking it. So I'm going to see if we have, yeah. So this is important. There is one of these for every motor. Any motor that is sold, you can find one of these somewhere. If you can't find one, you're not looking hard enough. But if you don't find one, you can make one pretty easily. It's not hard to make. Basically what it is the performance map. It compares on a motor, and this one's for a sim motor, speed, torque. This is just a different type of torque. It's just different units. Current, power, efficiency, and heat. Okay. So what you can do here is say, if I'm limiting my motor to 30 amps, let's go into the current column. We'll go find the closest thing to 30, which we can see there's 37.4 and there's 28.8.
Let's go back to third grade and do some rounding.
So you actually don't do rounding. Oops, didn't mean to make that little mark, but whatever. You actually do a thing called linear interpolation, which is a very crazy sounding term for something that's very easy. Basically, it's trying to find if there's this difference in these two numbers, what's the ratio difference between these two numbers, right? And so what you're trying to find is if I were to use 30 instead, what number would come out over here? Does that make sense?
So you would divide them and then whichever one's closest.
Yeah, basically. So if
oh, you do like 30 divided by 4.3 and then 30 divided by 5.7.
Not exactly. So basically you say 37, and I actually have to remember how to do this because I always get it confused because it's basically the same thing, but they flip around. 37.4 minus 28.8 is the difference between those two, right? And then you can either do from the 28 or from the 37 to find 30, right? So we're going to do from the 28. So 30 minus 28.8 equals the difference to your target, right? Which will be 2.2 and
1.2.
Is it 1.2? Yeah, you're right.
Wait, you can just do that by eye. That's an easy number. You can tell that 28.8 is closer to 30 than 37.
Oh no, yeah, this is not to find whether it's closer to 30 or not. This is to find the difference between your total and the difference between your target. So we chose 28 already for finding the difference because it's closer. Does that make sense?
It'll make sense once you explain more.
Yeah. So basically, and then 1.4 plus 7.4, so we got 8.8. This should be a 1. You get the idea. Okay, so now we have our total and our target change, okay? Then we have to do the same thing for the 5.7 and the 4.3, so, kind of. So 5.7 minus 4.3. That's 7 plus 7, basically.
1.4.
Yep. So that is our change here. So basically what we're trying to say is 1.4 is going to be equivalent to 8.8. So x is going to be equivalent to 1.2.
Wait.
So this is the total change. It's kind of hard to write with this. And this is the target change.
So
So what you end up doing is you divide and then find the relation. So do I have enough space? Kind of. We'll do basically 1.2 over 8.8 equals x over, what did I say? 1.4. So this is your equation. You just find x through it. So we'll do that real quick. It's going to be 1.2 divided by 8.8 times 1.4. So
wait, do you do the division and then you do the multiplication, or are we doing order of operations?
It in this case it doesn't matter because it's division and multiplication.
Oh yeah.
So 0.19 ish is the answer to that, and then you add that to your bottom number wherever you measured from, right? If we had measured from 37, we would subtract because we're going down, but we're going up because we measured from the bottom. So our bottom number is 4.3. So we can say boink. So the answer is going to be 4.4909. So I'm just going to round that to 4.5. Okay. So we can see now that is between these two numbers, 4.5. Okay. Does that make sense?
No. Why did you
Okay.
use 8.8? Is it 37.4 minus 2 minus 28.8 is 8.6?
You are totally correct. I always mess up on simple math, so thank you for catching me.
And where'd the hold on, I gotta figure this out.
That's fine. It's a very small difference there. So 1.2 divided by 8.6 times 1.4. There we go. So it's actually 195, and then we add to 4.3. So it's the answer is just going to be closer, honestly. So it's actually 4.4959. So I'm still going to round it to 4.5 for some.
Where'd you get 4.3 from?
4.3 is the bottom number of our torque over here.
Oh, okay.
So we're basically this 1.95 here is our change, right? And we're adding that to our bottom, which is 4.3. So we're increasing 0.195 up from 4.3 in the same way that to get to 30 from 28.8, we have to increase 1.2, right? So we're basically just doing ratios here and then increasing an equal amount in the two. Does that make sense?
Kind of. So we didn't use 5.7.
We did use 5.7, but that was just to find the change down here. So 5.7 minus 4.3 equals 1.4, which was our change, our total change. I'll show you on a graph because that'll probably clear it up a little bit. So if we have a graph here, right? And basically here's our line of words. Why can I not say words? Why can I not think of words? Torque is one of them, so we'll put torque over here, and the other one was current. There we go. Geez, thanks, brain. So if current is marked such, and torque is marked a number, basically what we're doing is the line, the slope of this line is the ratio between the two things, okay? So if I were to go to our next thing and we'll say 4.3 and 7.5, okay? So 4.3, or sorry, and 5.7, that's what I meant. If you look, that is right here, okay? Do you see that? It's kind of covered up now. I actually don't know how to erase with PowerPoint's eraser. Do you see the torque there?
What are we looking at? Oh, 4.3.
So on this table, right? Torque column right here. Okay. Do you see the 5.7 and the 4.3?
Yeah.
Okay. Those relate to the 37.4 and the 28.8. Okay.
Right. They're
Okay.
just ratios and stuff.
So if we make a graph where current is the x-axis and torque is the y-axis, then we know that 28.8, come on, let me write. There we go. And 37.4, okay? And I didn't draw this graph very well, I realize. We're gonna use a blue line. I'm gonna use the annotation tool, or a black line. So there's a point, there's a point, okay. That works. Very bad graph, but whatever. The black line here is the one we're looking at. Ignore the red one, okay? So basically what we're saying is these points relate to each other and these points relate to each other, right? Does that make sense?
Yeah. Yes.
So those were on the table, right? So if I make a new point here at 30, because that's what we want 30 amps for current, then what it's asking here is if I go and connect to this graph, what is the torque that I'm gonna get? We're gonna call that X, okay? Does that make sense?
What's the red line?
Ignore the red line. I just can't erase it for some reason. Pretend like the red line's not there, okay?
Are we ignoring the problem? Like you chose a sim motor.
Yeah, don't. This had more space on it.
Okay.
So just the graph here. Does this make sense?
Yes.
Okay, so basically the table, and then we're saying 430, what is the X, what torque do we get out of that? Okay. And so what we're doing is we're finding the slope of the line, and then we're using it to find Y, okay? So that is what, can I not? Oh, it's still in annotation mode, I see. That is what these equations are. Basically, and this is super messy now. Basically, we found our, I really wish I was using the annotation the whole time because, man, I need to find a better way to write on these things. Basically, we're taking our current, which is here in the current column. I don't know. Can you guys see my cursor? Can you see my mouse?
Yes.
Okay. So down here, you can see in the current column how there's 37.4 and there's 28.8. And in the same row, meaning related, the same amount, in torque, there's 5.7 and it's kind of covered up, but there's a 4.3 under there, okay? Those are related. So we put them on this graph, and then we need to find the slope of the graph. So basically what we say is we say 5.7 minus 4.3, right, is the distance in between here, okay? So that's our change, our total change, sorry. And then we say 37.4 minus 28.8 equals our total change on the bottom axis. And that is the distance between here, okay? And now what we need to find is the change between 28.8 and 30, because that's what we actually want. So we do 30 minus 28.8. So that is our target change. Okay. And then we need to relate it to find the distance here, okay, which is between 4.3 and our x. Tell me if any of this doesn't make sense, okay?
Okay, can you just hold on a minute?
Yep. Jude, Maxim, are you guys following along okay?
Yeah.
Yeah.
Okay.
Good? Okay. So does this make sense so far?
Yes.
Okay. So if we take these guys, we're gonna actually, I'm just gonna write I'm gonna say total y change and total x change. Basically, what we're trying to do is find the slope of this graph. And so what we're gonna do is we're gonna say x. I really shouldn't say x just because we're using x somewhere else. So we'll say torque, the torque that we want, which is this thing, over our total change on the y-axis is equal to our target change on the x-axis divided by the total change on the x-axis, okay? And what that ends up equaling is torque over 5.7 minus 4.3 equals 30 minus 28.8. That's a minus over 37.4 minus 28.8. That's really hard to write, but can you see this? Basically, how this works?
30 minus 28.8.
So what's important is this equation here. The numbers are just our example numbers, okay? So, yeah, and we might actually should have some linear interpolation homework depending, but we'll see. So does this make sense? Let me know if it does not.
Yes. And then we would go ahead and fill in like 5.7 minus 4.3 is
Yeah, so
1.4.
that's 5.7 minus 4.3 is the total change y. 30 minus 28.8 is the target change x. 37.4 minus 28.8 is the total change x. You would do all those by themselves, and then you would do the multiplication and division, okay? So what you would end up with is 1.4 over, what did I say, 8.6 equals Actually, was this 1.4? No, that was a 1.2. Sorry. Equals torque over 1.4. Sorry, I know my everything's kind of messy, but do you see how this gets there?
Yes.
Was someone else about to say something? No? Okay. So then you would divide these two and then multiply this by whatever is over there. And what you end up with is 0.195 approximately, okay? And that is this change here. See that? So if I want the actual value of this from 0, then I have to add it to 4.3. So we're just going to do plus 4.3, and what that gives us is approximately 4.5, okay? And so that is our total answer there. 4.5 is our end answer. For how much torque do we get out of 30 amps, okay?
Wait, so it was 1.2 divided by 8.6.
Mm-hmm.
I got 0.139.
So 1.2 divided by 8.6. Yeah, 139.
And then you'd multiply 1.4 by it.
Mm-hmm. So you get 0.195 and then some extra stuff.
Oh, and then you add.
And then you add 4.3.
Wait, why?
Huh?
Why?
Because your change, your 0.195, is just the distance between here and here. Do you see that?
Okay, yeah.
And so to get the actual distance from 0, you need to add the 4.3 that it's coming from, right? So your total answer is 4.5. All right. Does that all make sense? All right. This is super messy.
Yes.
We're going to try to clear the annotations and see how much. That cleans it up a little bit. So real quick, so we now have our torque. That's very cool. We also need power and stuff, but we might skip that for a sec because that's more linear interpolation. Basically, what this map, though, does is you can say, here's my limiting factor. In this case, our limiting factor was current. So how much of the other things do I get for that limiting factor, right? Technically, we could run it at lower amperage, so we could do anything under that as well, but there's not really a reason to. So in this case, we're running it at 30 amps. That means we get 4.5 inch-pounds of torque. We could also find from this how fast it's going to be. We could find how efficient it's going to be, which in this case, it's going to be about 60% efficient because we chose a 60% efficient area. We could find out how much power it outputs and how much heat it creates. This, I know, is a little daunting looking. This is a this is basically that table, but in graph form. So this is a performance characteristic graph. And what it does is you have your torque in foot-pounds down here. So torque is on one axis. And then you can put different things on other axes if you want to. But basically, there's a few different things to notice, some trends to notice. The first one is the one that we just did. The higher your current, the higher amperage, the higher your torque is going to be, okay? So if you put more current in, you're going to get more torque out, okay? Your horsepower, which is just your power, right, is going to follow sort of a upside down parabola. So it's going to go up. So your torque is going to go up and your power is going to go up. But then it's going to reach a point where it's going to fall back down. You're now going to be running it past the point it's supposed to be running at. So it's going to go back down. So the more torque you get, the more horsepower until you push it past a certain point and then it goes down instead of up. Does that make sense?
Yes.
Another trend, which is one that is pretty simple, the more torque you get, the less RPM you get, the less speed. So as torque gets bigger, speed gets smaller, okay? And then the last one is efficiency, which basically you can see here, the efficiency curve. Efficiency goes up really quick and then starts to go down after that. And the reason that we always talk about 60% efficiency, so if you see, this is 60% efficiency. We draw a line right here. We can make some assumptions. Basically, we'll be saying that its peak power is not at 60%, but peak power is also not where you want to be running, usually because you're going to have a lower speed, etc. Depends on your applications, but peak power, usually you don't run it there. Why? It doesn't really matter. Its peak power is usually around 60% efficient, but we want always, and we'll see this in a bit, we always want to be operating on the left side of this graph, okay? So if I were to draw a line down the middle of this graph here, right, from the middle of the parabola, we always want to be on the left-hand side, whoops a doodle, the left-hand side of this graph, okay? So always stay to the left. Reason why is because when you're on the right side of the graph, that's when your motor is starting to die, okay? The reason your power is getting lower is because the motor itself is struggling, okay? So you always want to be on the left-hand side, never on the right, because you don't want to burn out and kill your motor. Meaning, in this particular case, this motor can put out somewhere between 0 to 10 foot-pounds of torque and still be okay. And you can also see RPM-wise, if we just draw a line here, it'll run somewhere between 1,500 and about 3,500 RPMs, okay? So the graph is nice just to visualize how the motor works. And most motors will have this performance map, this performance graph, wherever they're being sold, so on their website or something. So quick things on motors, and you can see this on the graph a little bit, is first off, max power will occur at 50% of your stall torque. So stall torque is basically how much torque the motor is putting out when it can't move anymore, right? So that's the maximum amount of torque it can create. It's also about 50% of the stall current and 50% of the free run speed. So 50% stall current is how much current you can put in before the motor stalls. 50% free running speed is if I took the motor and just ran it without anything on it and put it as quick as it could go. That's how fast it would be spinning, is the free running speed. Basically, we always want to be running below that 50% line, because that means we're not burning up our motor. Basically, there's two different operating conditions. You can either have high speed and low torque, or you can have low speed and high torque. That was the trade-off that we're talking about earlier. And your max efficiency occurs at around the 25% of your stall torque and 60% of your max power. So you can see that here, efficiency peaks out pretty early on, right? And what efficiency means in terms of this is how long your motor is going to last. If you're running it at really high efficiency, then it's going to last a lot longer than if you run it somewhere else on the efficiency line. Okay, so rated load is like, you know how the chains we were talking about working load, and that's like industry, how long it's going to last. The rated load is the same thing. It's how long, whenever you see like this motor will last 5 years, they're talking about the rated load. So if you were to run it at its rated load, it would last that long. usually this line that I drew here in the middle, people will run it typically somewhere around here. And the reason why is because you get a pretty good trade-off of things. You stay high on your efficiency curve. You get good power out of it. Your RPM's pretty high and your torque is pretty high. So that's a good middle ground. You can run it lower if you want higher RPM and lower torque, or you can run it higher if you want more torque and lower RPM. Does that make sense?
Sure.
I know that's a lot. We can go through other things and do reviews if we need to. We're not going to do that right this sec. Oh, wow, transitions.
Hey, are we going to go over class schedule? Because
yes.
Okay.
Those are good, but we're not going to do them right now. Checking the time. Motor parameters. Yeah, we'll look at this real quick. Basically, this is what I was talking about. Motor parameters. Based on the manufacturer that you buy from, they're going to show different data. Andy Mark, Rev, Modern Robotics, they're all good about putting out their stuff specifically because they cater to first. If you want to,
Rev has some inaccuracies on their site, and you can find those on Discord and stuff.
You can also test it yourself, and that's actually what this is for. If you want to, so like this line here, basically, it's not that difficult to test. You really only need 4 values to predict your best performance. You need its full speed with no load, so you get your motor speed and the current. So you run it as fast as it'll go with nothing on it. And that gives you your highest RPM with no load, and it gives you your highest current that you can pump into that thing. And then you also need your maximum torque, which is your stall. So basically you want to hold the motor or put something on it so that it can't move, and then push as much current into it as you want and measure how much torque it's putting out. There's a lot of ways to measure torque, but you can set up whatever system you'd like. So if you measure basically its top speed and its stall torque, its highest torque, at its highest current, then you can figure out its whole performance map from there. And you can make your own table, you can make your own graph, all sorts of things. This just shows the setup. They seem to have a Teijin, so like a window motor hooked up to a torque setup to measure how much it will put out. This is what we were doing a little bit ago. So basically what they are showing here is this is their stall torque, this is their highest current, this is their lowest current, and this is their highest RPM, their free speed RPM. So this is if you were doing it yourself. Basically what you do is you just choose an increment. It looks like they've chosen an increment on, what did they choose an increment on? It looks like current? No, I don't know. Basically, oh, it looks like RPM actually. Yeah. Yeah, so they've gone basically by 3s every step on their RPM. There are some differences, like there's a 44 to 48 there, but basically they're going 3 RPM each time. So they've chosen a increment, and then they've just 48, and then however many data entries you want. So, and you find that, and then you can say same thing for your torque and extrapolate it down to 0. 48, you can go down to 0. Current, you go from your highest current to your lowest current. And then everything else you can find from those things. Power is just your speed times your torque. So you multiply those together and you get your power. Efficiency, there is an equation for it. We're not going to do it. And heat, same thing. So if you want to, you can definitely do this yourself for motors if you can't find stuff. This is the performance map for that motor. Basically, this is just them entering their data points and creating a graph off of it. And this is at full voltage, so you could do it at different voltages. Yeah, these are quick things as well. Basically, max torque will occur when there's no speed, so 0 RPM. it will produce 0 power and all thermal power when you do that because it's just stalling out. If you do like lightweight motors, so like this shows a blow dryer or something, they'll burn out really quickly. So don't do this to like a servo. That would be really bad. Before we continue past here, actually, I think this is where I'm going to stop for today, because past here is more like suggestions, and then we're going to get into stuff where it's actual math. So well, let's do questions, and then I'm going to talk about class schedule and things like that. Okay. So does anyone have any questions about the class, about things that we've covered today, or anything like that?
Oh,
Okay, Maxim, Jude?
Yeah.
Nope.
Cool. All right, well, let's just talk about class schedule then. So class schedule, basically, we're always going to be doing Wednesdays from 1 to 3, as usual. However, because it is the end of summer and school's starting up and I'm going to be moving back to Massachusetts, we're going to have to figure out how this will work if we want to continue into the school year, or if people don't want that, that's totally fine. Currently, I'm planning to have 1 or 2 more classes. It depends on when I go back up to Massachusetts, because I will not be able to teach the week that I am driving up there. So next Wednesday's class is definitely going to happen and may be the last class. If people can't make that class, or if people want to do another class, we can put one on that weekend as well. What do you guys think?
so next week I won't be able to be here. And also I don't know, because this year I'm moving it up a grade we're doing we have a bunch more homework and my classes are more advanced. So I don't think that I would be able to concentrate as much on this in the school year, no matter how much how much I like this.
Jude, Maxim, you guys have any input? Couple weeks and such?
Yeah, I don't know. All my classes seem pretty easy, so I don't know if that'll be a problem for me. But
I also
yeah.
need to talk to Kyler and Mr. Smith and everyone as to what the post is doing in general.
Yeah, I'll have school on Tuesdays and Fridays.
And obviously I'll have to fit it with my class schedule as well, but we can go over all of that and figure out a school year plan if we want to. Because the thing is, Jude, I think in one of the meetings you commented like the one meeting I come to a year or something. It's totally true, but the reason why is because
Sorry, you cut out like really badly there. I didn't hear anything.
You joked one Thursday night meeting, that it like the one meeting I come to a year, which is totally true, but it's because I live in another state.
Well, yeah, I wasn't trying to like.
No, I know. I thought
like,
it was funny.
David,
but the thing is, I would be totally down and would love to teach a class or do something online if I can, because that doesn't require me to drive to Oklahoma. So if I can continue to teach and do stuff from Massachusetts, I'm super down to do that. We just need to figure out a plan between the post and Kyler and your dad and what we're doing on all that. So I'll figure that out with them for the school year. These next 2 weeks, definitely plan on class on Wednesday. I would suggest trying to get a few other people from your teams. I know that, well, Maxim and Jude, you guys are on the same team.
No, not since last year. He moved to Leviathan.
Oh, okay, cool. Well, then try to get people from your teams, Maxim, Leviathan, Jude, Project Peacock, and if either of you can, try to reach out to MassFit people. Try to get people to come to this next class on Wednesday, because what I'm going to do on that one is more like suggestions in terms of FTC as to what motors to use for what things, as well as how to like really choose based off of exactly what you're doing, which I think is going to be the most useful in terms of FTC. It will be a math light session, so there won't be that much math if that's a selling point for people on your teams.
I like the math. That's actually why I'm doing this. The
Well,
math.
I mean, there's always going to be a little bit of math, but this one's going to not be very much at all. So the more people that can come and learn that, I think the better for you guys, because it will make prototyping easier for you. People will make prototypes that more likely work than not work. That's what I'm going to
So-
try to do with the next class period, is set you guys up to be ready to just not necessarily work out all the calculations with that class, but to just know what to try to use and to put something together. So that's going to be more of a prototyping class than anything. Okay?
Yeah, in FTC, like the thing we really need to learn more is like how to build stuff that can properly take loads, because like every time we've ever
And
used a drawer slide, it has broken very
the
bad.
biggest thing with that is statics, which was the first section of the class. The thing is, and this depends, is I know that math for a lot of people can be boring. I hated it when I was in high school and middle school. Well, okay. I liked it by the end of high school, but in middle school I hated math. The problem is, if you actually want to do something correctly and know that it's going to work in engineering, you have to do math for it. FTC is simple math, but you got to do the math for it if you want it to work. This next class is going to be not very much math, very FTC focused. So I would like as many people to show up as can. I would say Maxim and Jude, you guys should push for your team members to come to that class. Past that, if I have another class, we're going to do more motor math, so that you guys, and if anyone else wants to come, will know about motors specifically, and I'm going to focus on FTC motors. So I'm going to pull lists of all the available FTC motors and show you what exactly runs well for what, right? And how to know how it runs. Also how to gear it for those things.
Aren't all of the FTC motors basically the same, and the difference is just the gearboxes?
No, I mean, yes, if you're all from the same brand. So like if you buy all Andy Mark, yeah, they're all the same. They just have different gearings. But if you buy like, you guys said you had modern robotics motor. So if you have a modern robotics motor versus a Andy Mark motor, they could be different. They may not be that different, but they'll be a little different.
Yeah.
Another big thing, the Tetrix motors that we used.
Oh
are
yeah, those
way different.
Those are way less powerful. Yeah.
They have horrible powers and horrible efficiencies, but like you can see that by looking at their maps. So you could actually look at all the performance maps of all the motors and choose which motor is the best motor. Like we've been moving motor to motor, but if you actually want to compare them, you could, and get the best one. I'm also going to look at all the servos and stuff. Like I'm going to do this kind of on my own time. Look at all the servos and find which things are best for high RPM applications and which ones are best for high torque applications. And try to kind of do a lowdown on those.
I know the most powerful, like in quotes, ones are the Andy Mark ones, but I thought that was just because their gearboxes were more efficient.
Probably not. It's probably the motor itself, but I'll look at it and let you know. I'm gonna basically give my general inclinations next class. Just say like if you're doing high RPM, use this one. If you're doing low or high torque, do this one. Not showing the math for those, but the class after we're gonna actually compare and look at things.
David, you haven't messed with core hex motors, right?
I've seen them.
They're basically just two servos.
David,
Yeah.
I gotta go do something, so I'm gonna have to leave the
Basically,
meeting.
next class, 1 to 3, Wednesday, try to get people from your teams to come, okay?
Okay. Thank you.
Yep. So Jude, Carson, basically after that, the next week is up in the air. I don't know. Moving during that time, we'll find out. If we do have class, that'll probably be a pretty math heavy class, and it will probably be our last class, but I'll try to make it as interesting as possible and throw in some like prizes and stuff.
Awesome, sad, and awesome.
So if you can get other people to come to that one as well, but I understand that if it's math heavy, that people might not want to come. So put it out there. That's kind of the plan. I'm going to talk to Kyler and Mr. Smith and people and see what the post is planning to do, and I'll let you know one of the next Wednesdays as to what we're planning on doing. So
Okay.
yep. So that's class for today. Thank you guys for coming, and we'll continue next week. I guess Carson will continue for you 2 weeks from now.
Yep. All right. Bye-bye.
Awesome. See you.